First couple of slides, and the first thing we wanted to talk about in data cleaning is, Heather, do you want to?
Yeah.
So is about, we're first going to speak briefly about data entry that Heather is going to talk about, since she is the expert on that. And then I'll move on to talking about other forms of data cleaning once the data is already input.
So I'll make this pretty short. I mean, the need for data entry is, we need it less and less because a lot of the data are being directly input into systems. They're not being entered off of paper. But when you're taking a look at data entry and the quality of what you're doing, you want to look at it while data collection's ongoing, because it does give you feedback about how your forms are being filled out. So if your data entry person says, I keep finding that I can't, this item is always missing, or I can't read the way this person writes her numbers, then that's an important piece of information to look at. Just like with all other QC, how much of it you need to review is completely based on how important it is to your study. So looking at about 20% of the values is a nice place to be, particularly if you have like maybe less than 200 records, because each record is of importance. But if you've got something that's your primary outcome, you might want to review 100% of them just to be sure that they're in there right. So kind of evaluate what you're looking at and how much possibility it is that there would be an error. And then determine how much error you can tolerate. So like, are you satisfied that 95% of all the values that were entered correctly? Or are you going to shoot for 98 to 100%? So I tend to go with about 98% because I figure 2% off, you can tolerate it. But for things like, there's some messy stuff like diet histories, I would go with 95 because those are just so full of a lot of different kinds of data that it's easy to be off by just a little bit. So that's what if you're having somebody enter data, you want to make sure that you review it and take a look at it. So there's two ways to take a look at that quality. One is that you can take your data forms and you can have a printout of your database and you can just compare them, right? One person, you have two people, one person has the data form in front of them, the other one has the data entry in front of them, and you're just ticking off the numbers. The other option, and I still need to sort out how you can exactly do this in REDCap. I have a couple of ideas, but what we often do is that you re-enter a set of forms. And so then you can compare them and you say pass 1 versus pass 2, and you compare them using a data management program like SAS, and it'll spit out the differences for you, and you don't have to do that ticking through. And it may be simpler for someone, a low-level person, to just go through and re-enter all the data. And if you get 100% match, then you don't have to check anything else. So if you find differences, you have to decide who's going to adjudicate them. So figure out who can determine what the correct value is. And I would argue that you want to have someone of a fairly medium to high level determine what that correct value is. You don't want the data entry person determining what the correct value is. You want a study coordinator, someone who can really evaluate and understand what that data element should be. And then you want to calculate an error rate. So let's say you did pass 1 versus pass 2. If you found errors and you looked at it and, oh, it turned out pass 1, the value there was the one that was correct and pass 2 was wrong, you don't want to count the pass 2 because that's not your primary data. So throw out those errors. You only want to look at an error if it came off of the pass 1, because that reflects the error that's likely across all of your data. And then your denominator is not the number of people, it's the number of actual values you're looking at. So if you have a simple demographic form and you have 10 items on it and you have 10 people, 15 participants, your denominator is not 15, your denominator is 150 because there's 150 places where there could have been an error. And so you want to make sure that you're accurately reflecting what that error rate can be. Depending on how big your study is, you may want to look at data entry errors by the data entry technician, because some people are better than others. By form, some forms are more difficult than others to fill in. And then if you have a multi-site study, you may want to look at it by site, again, for all these differences about where people could have it. So what happens if you find an error rate that shouldn't be below your tolerance, it should be above your tolerance? So you decided, I'm happy with a 5% error rate, but you find that you've got an 8 or 9% error rate, then it means you have to re-enter all your data because you just can't be sure. Either re-enter or you have to do a 100% check of your data. It means that there's a level of error that you can't count on.
Great.
Is that it? Did I have any other slides?
Yep. Nope.
Okay, cool. All right.
Okay, good. So your data are entered. Now, what do you do, right? So data cleaning and manipulation. So there are, first of all, for those of us who are not going to be doing data analysis, why do we care about this? And for those of us who are using secondary data, why do we care about this? Because we just assume data are coming our way and cleaned and everything, especially if they come from these, large epidemiologic data sets, CDC data, etc. There are many reasons we care about data cleaning. And like I said, the more you do at the front end, so the problem is mistakes can be made throughout this whole process, right? But our problem is not making mistakes, it's how we identify mistakes that are made. So the ability to identify mistakes is not that simple. We can have a mistake that we're going to see some of these kind of errors that we may not be striking, and so may get lost in the kind of analysis, especially when we use continuous measures. So how do we identify error? Well, one of the things we want to do is really think about the data we have once it's entered before we actually begin. And there are a lot of different ways people do things. This is the sort of outline steps that I would take and that I think kind of make sense. And of course, this order is, just kind of logical to me, but it's not set in stone. It's just a suggested guideline. But in going through these steps, I want to point out some of the potential for error and some of the ways we need to think about our data. So the first is identifying variables, measures of interest. This might be really simplistic and obvious, but I kind of want to go through it anyway. It might be redundant with some things that you know, but I think it's important to identify these variables in order to get to the next steps. The next steps are, we're going to talk about missing values and what that means, skip patterns, how we might go about doing some recoding, what it means to have valid data, and we'll discuss very briefly how to prepare for data analysis. Okay, so level of measurement. A continuous measure is an interval or ratio. We're pretty much all familiar with it, right? So systolic blood pressure, CRP levels, like numbers that are on a continuous spectrum, okay? Categorical variables are either dichotomous or binary, yes, no, or else have multiple categories. Now, if they have multiple categories, they could be one of two types of variables. They could be nominal, which means there's no order involved at all, okay, such as race. They can be ordinal, which is the other kind of option, which means that there is some sort of order inherent in these levels. So obvious examples of continuous measures listed here, I kind of mentioned them. Categorical variables. So these are two types of commonly used dichotomous measures. So one is gender or sex. Here it's 0, 1. By the way, note coding values, okay? People do things in different ways. So data sets will input data in different ways. Sometimes gender will be 0, 1, 1, 2, could be other numbers, right? Don't just take for granted. Do not guess. Do not guess, okay? There are some standard ways or ways that you think make sense to you. It is by no means going to be, like the determining factor in how things are done. Never guess. Always go back to the documentation, to the code book. I've been in situations where I just said, I'm not going any further in this analysis if we don't have any more information, because it's just not, it doesn't make sense to guess. This is really important for dummy variables, right? So we're going to talk about that in a minute. But when you put, for example, if you are going to put that variable gender in your model, okay, so depending on the program you use, programs will generally consider the higher number versus the lower number, or 1 versus 0. But some procedures, depending on the software program, may do the opposite, right? So you generally, we code dichotomous variables as 1 versus 0, and that's what's going to happen in the model. If it's 1, 2, you're not sure how the model's going to deal with it, depending on your software program. So it is for dummy variables, what we call, kind of the binary variables, is important to code 1, 0. Here, for example, asthma, 1 is yes, 0 is no. I've seen it the other way around, right? So keep that in mind.
For jump, I think it default codes this way,
Okay.
0, 1. You can tell it to do, was the other one, effect coding or whatever, 1,
That's
2.
when you input your own data.
Yes.
So if you got a
yeah.
data set from
You
somebody
get it,
else,
it's going to have one of these already.
it's going to have something.
Yeah.
It depends what they did,
That's right.
Yeah. And by the way, I've gotten a data set where, for example, gender, male and female, was text form. I converted it to numeric. And then I had a problem because they had input female in caps, female in lowercase, male in caps, male in lowercase, mixed caps. That comes out to 5 gender groups, right? So programs don't have brains like we have the brain. So we have to think things through. This is an example of a nominal measure, so it's marital status. So nominal measures are, again, no inherent order. They are numeric. Here you see numbers ascribed to the different values. And if you put them in a model, the model doesn't know what marital status is, the software program. It's going to assume an order if it sees numbers 1 through 9, okay? Including 9. 9 is don't know. 7 is refused. The software program does not know that, okay? So they will just see this as an ordinal variable. So it's really important when you look at these measures that you think through, how do I want this to eventually, how am I considering this variable? Nominal, ordinal, etc. Okay, an example of a categorical variable that is ordinal is self-rated health, right? So we have these options, excellent, very good, good, fair, or poor, and we have refused and don't know. So what numbers here, what range of numbers is in fact ordinal?
Just a 5.
1 through 5, right? After that, 7 and 9 are refused and don't know. Again, the software programs cannot distinguish between this, right? So they will just assume refused is a lower level, don't know, a lower level, right? So you have to recode out the 7 and 9, and we'll talk about that with coding. Okay, that's really important. Okay, so how about other examples of levels of measurement? So continuous scores, we talked about some potential biomarkers, BMI. Other continuous measurements can be scales that you create, that have been created. An example of this is depression scale, socioeconomic score. Let's say you created a score. Let's say Todd created the, your clinical score to identify dental implant failures, right, or the risk of dental implant failure. So once you've created that score now functions as a continuous variable. Other algorithms that have created scores are like, for example, BMI, right? So body mass index. Those are taking two continuous variables and recreating them in an equation to a single BMI index. That index is still a continuous score. Pack years of smoking, right? So if you're gonna, you don't want to know if someone's just a smoker, you want to know how much they smoke. So that's the packs that they smoke a day times the years that they smoked, and that's pack years. Okay, so now I've taken, now when I think about smoking, I could either think of their current smoker, former smoker, or else I can consider pack years, but those are two different types of measurements. So an example of the summary scale, and this is what we taught, this is Framingham. So Framingham is when you create the equation, you end up with points that then get translated into percent risk. Now, we did a study where we wanted to use Framingham, but we didn't want to use it as a continuous variable. We wanted to break it into levels of risk, right? So then we took that and we broke it down into low risk, moderate plus risk, high risk, very high risk. That becomes a categorical variable, but an ordinal one. So we actually can keep this in a model as an ordinal variable, which functions statistically as a continuous variable, right? Because you just put it in with the kind of just, instead of a range of whatever, of like 0 to 100, there's a range of 1 to 6, right? Or you can break it up into the individual units and think of them as dummy variables, right? So you can compare very high risk to low risk, high risk to low risk, right? So, and you guys have learned about dummy variables. Have you learned that before? Okay.
I don't know if I've heard that term specifically. The concept makes sense.
All right, so I'm going to show you more examples of that further down. Okay, so we talked about continuous ordinal. So those are levels of measurement. Now, what about the next kind of stage? So you've determined what variables you're using, you determined the level of measurement, you're clear about sort of how you want to consider each measure. One really important issue is missing data, okay? And the reason why it's important is you kind of have to think of what you're going to do about missing. So first of all, it's a red flag. Why am I missing these data, okay? And obviously, if you are missing on your main factors of interest, then you're in trouble, and you need to figure that out before you continue. And people are going to drop out, so you're not going to have the same sample size you thought you had. The second issue is, what are the data that are missing and why? What happened? Why did it happen? And now, once we've figured out how it happened, if there's nothing we can do about it, what do we do? What do we do moving forward? What do we do from a statistical perspective? Imputation methods are becoming very popular, but before we just use an imputation method, we want to think about what makes sense, right? Because imputation carries a lot of baggage with it, right? And it could be potentially lead to selection biases. We want to think through how we do our imputation. Okay, so let's take a look at some missing data. So we have, these are biomarkers. This is from MIDAS. You can kind of see by the last three characters in each of these variable names. So the top one is age, BMI, LDL, HDL, and then kind of a recoded measure. So pretend this is just the data set you got, right? So you're getting these measures, and you see the last variable was recoded. Someone recoded that with MSG, with missing, okay? Okay, we're not quite sure what that means. But we see our N, so we've run this in SAS, it's called like a proc means, and we want to just look at the N, the sample size, the mean, and the median, okay? So we see that for every biomarker, we have a sample size of 734, except for triglycerides, it goes down to 732. Okay, so 2 are missing. All right, that's not too bad, but we want to know what's happening. So if I look at this, I'd be kind of surprised that no one's missing on the other measures, because that's usually unlikely. Usually everyone has age. Depending on the sample, a lot of people tend to be missing fasting variables like LDL. So that would be kind of a red flag for me. Unless I go back to the code book and I say, okay, they did a really good job, everyone fasted, fine. But okay, so that's my first impression. Okay, so I don't really see a problem here. Okay, I don't see any particular problem. But the issue is, what didn't we look at when we looked at N, mean, and median? What didn't we look at? What might be helpful here? Well, yeah.
In terms of determining missing values?
Yeah, just interest. What are the first things that
The
you
distribution.
Right, so the full distribution. So first of all, I want to know the range. I want to know what my minimum value is, what my maximum value is. I want to know the standard deviation, right? So this is not the full distribution. So let's take a look at the full distribution. Okay, so these are kind of small numbers, but what stands out at you? You see from back there?
Yeah, enormous range.
Okay, enormous range. Now let's look at the values themselves. So people can be ages 37 to 86, okay. BMI of about 18 to 64. 64 is pretty high, but I guess it can happen. Okay, how about LDL? 16 to 999.
This is weird.
Something looks really
Like
weird.
there's a ceiling.
HDL, 9999. What is that? First of all, this does not look like a real number, right? I mean, age, it makes sense because age are whole numbers, but these should be decimals, LDL and HDL. So
The other thing is, why are there so many decimal places? I mean, it's a minor
that's
issue.
that's just an issue of the statistical package. So,
Right.
for example, here, so SAS in this case will read it as a decimal. Okay, so it's especially because it could have been input as with a decimal, probably not with age. Actually, this age I think is a calculation of their date of birth, of the date minus their date of birth, so that will come out as a decimal. So that's less important.
Right.
These software programs are just going to add as many decimals.
Oh, so this isn't from the paper.
No, this is an output from SAS.
Oh, I see. That
So
makes
I've
sense.
taken the variables that I got. I ran a
That makes
procedure
sense.
to look at the distribution.
Oh, I thought this was
Yeah.
cut from a paper.
No.
That was a little-
No, this is SAS output. Should have made that clear. Okay, so 999s. Very strange.
There- Somebody was using that as a filler
For
no entry, probably. You can see the mean is shifted just slightly higher. So it still actually looks pretty normally distributed based on the mean and the median, but then you have literally probably one or two
exactly.
dummy variables.
Right. So they're not dummy variables. Or one or two outliers, but they're not outliers. They're actually missing.
Yeah.
Meaning you want to look for outliers here. You want to look for that weird, really high number. Like let's say there was an LDL of 500, right? That's not really that's past the threshold of the assay. That's an invalid number. So you can set that to missing. In this case, if you look back at the documentation, you'd see that 999s mean missing. Now, what happened was Midas provides their data very clean in Stata form. And Stata recognizes you can put in their missing values. When you transfer that to SAS, it doesn't always get translated. And so SAS just sees the 999. It's not set to missing. So that was and that's just the way Midas operates. They create this missing data. I receive the data from them. It's my business to find out what is missing. So that's why this, going back to the documentation, looking at the range is really important. Jenny, were you saying something? I heard some noise.
Yeah, I said that there's probably missing data. So
Yeah, exactly.
because Dr. And also he told us about that issue.
Yeah. So you're saying that you've been told about this issue when you receive data?
Yeah, we had a lecture with Professor Ellershoff.
Oh, we talked about this. Okay, good.
Yeah, about the 999.
Right. So in this case, what's tricky is it's not only 999. If you actually look at the data set, and I don't know if I provided the code book, it's also 998s. And confusingly enough, sometimes they messed up and they used 99. Now, 99 is a valid number, right? So data like centers mess up, okay? Data sets, doesn't matter if they had a coordinating center, they can mess up. So you do have to kind of look back, possibly contact them. In this case, it wasn't only 999s, it's also 998s. And what we do is if we recode out, now it turns out this recode out missing, if I look back to what was done before, that's exactly what they did. So I did this again for LDL and HDL. I coded out the missing, and lo and behold, we now go from 734 to 732. So these guys, LDL, HDL, triglycerides, probably people who had compromised fasting levels for whatever reason are missing. Okay, we don't necessarily know the reason. And the maximum goes from 999 to 283 here and to 121, which looks reasonable. So again, now these are non-missing values, and I still want to look for outliers. Outliers might still be relevant, but at least I know that I've coded out the missing. Okay, so how about this? This is a set of measures of income. Okay, so all these are different measures of income, total earning income, the respondent's income, the spouse income, household income, all these are measures of income. Okay, so in my just looking at the means and the medians, does anything stick out?
It's highly skewed.
Right, well, they're very different, and look what the mean here is. The average income, the average spousal income here is $1,100,000. That should raise a red flag, right? That's not common.
Maybe West Side LA.
Right. Total household earning $916,000. So something strange, especially if the median is so much lower. Okay. So, in fact, the maximum here was 999999998. Okay. That is going to, as opposed to before, where we couldn't really notice a difference because there's only one person and it was 999s, which isn't so far off in the number of digits. Here, it's so far off that it becomes an egregious difference. So you're likely to spot this, but you still have to look out for it. You have to think about what the data mean.
Is this your typical methodology for initially looking for just doing initial screen of outliers just to run this?
Yeah.
Or do you look at the physical distribution?
So people like doing different things. I like doing it both ways. I like looking at the numbers themselves, and then I'll run box plots or histograms.
Okay.
I think that box plot, it's up to you.
Okay.
To me, I like to look at the numbers because I think sometimes with box plots, you'll see, like depending on how big the resolution is, you might see a little dot on top, you might not.
But
you don't even know what the number is. Like you're going to end up doing this anyway.
Yeah. Okay.
So yeah, I'd recommend going this way. Okay, so we set this to missing, and lo and behold, the maximum is it's much different, right? So the average income becomes 42,000 instead of the 1 million, right? Instead of the 80,000, the 1 million becomes 28,000, right? And the maximum is 200,000. So very, very, very different than before.
In your data set, so you would have, say, your first the R total income, and then you would insert like a new column right next to it where you recoded. Is that typically how you would handle the data management?
You're picturing an Excel file, right?
Or jump file, but yeah, same
and the
idea.
jump file looks like Excel.
Yeah.
So
just so.
In SAS, when you have like huge data sets with many columns, you don't really work with the spreadsheets. You work with in kind of an environment that's more like coding environment. Okay. So, but yes, essentially that's what it's doing. When you create a new variable, it's creating a new column.
Okay.
Yeah. All right. So, what about categorical measures, right? So we looked at self-rated health. This is NHANES, and like I said before, 1 through 5, we know. Because we're familiar with the outcome, we know how we want to think about it. The range is 1 through 5, is excellent through poor. But when we do like a frequency distribution, which you really want to do of all the categorical variables, we see there are more levels of these values that we didn't expect. And here it's refused and don't know. Now these could be very valuable. You could want to know if someone is just missing, if someone actually refused the question, if someone didn't know the answer, those might be relevant to you. But in any case, you want to remove them or somehow distinguish them from the ordinal values, right? In this case, I would just set these to missing. So, and the other thing I would do is, I kind of, when I look at categorical variables, I look at the percent in each level. So these look pretty good to me. There are enough people here. This looks too small. I don't want a category of only 2%. So to me, fair and poor, I'm going to collapse them. Okay, that's just a decision I made. If you have reason to keep poor separate, that you can. Numbers tend to be, it tends to be better to sort of have bigger cells, depending on what your reference is, etc. But there's no reason I had to do this. It was just something that I only decided to do when I looked at the whole distribution. Okay, and these refused and don't know, I would definitely set to missing. Okay, so another kind of example is marital status. So what do you see here? What would you do here? Well, what's the problem, first of all? We have 6 levels, right? And they were ascribed like numerical values, 1 through 6.
There's a weird 7 category.
There are 4 people that were given the value 7, 7. Right? Now, you can say to yourself, you have a couple options. You can say like, well, obviously they meant 6, which is not that obvious. Never guess, okay? Even if it was 6, 6, I would not guess and make it 6. Like, it's just, you don't know what was going through that person's mind. In this case, this is NHANES. I'm never going to find out the truth because there's no way I can get to a person in NHANES. I know that as the researcher. If it was a smaller data set that I can go back and check, then I will go back and check. But if I can't, I would treat those 7 7s as missing because I don't know what happened to them. And I can't guess. Okay? So those I would set to missing. The other thing I might do here is think about what I actually want to look at, right? So these are a lot of different variables. I may, for my purposes, I may be just interested if someone's living with a spouse or partner, in which case I would put married, I would leave married on its own. And then I kind of, maybe I don't care about why they're living alone or why they're not married or why they're not partnered. So I would put together widowed, divorced, and separated. Okay, so I have to think through, and that would give me kind of more equal groups too. That's another plus. I would put married and living with partner together. So you kind of have to think through what is the purpose of your variable and what can you do with it. Okay, so what I had said in the beginning is what variables are missing. Now, sometimes you don't know, but why are explanations important when you can find out? So this is an example, I think I mentioned this. These are MESA data. MESA over 5 waves of data. So each of those numbers, heart rate 1, 2C, 3C, 4C, 5C, represents 5 visits that were about 1.5 to 3 years apart. And I'm looking at the ends, totally what I expected. I know this is about the whole sample, and I know at each wave people drop out. Okay? But I have a problem because I know at each wave people drop out, but this does not make sense to me. Because why would I have this massive drop at visit 2, okay, going from 6,700 to 5,000, and then it goes up again to 5,900. Now, I know MESA because I did my research, and I know the code book, and I say to myself as the researcher, like, this doesn't make sense, it doesn't jive with the data. I need to find out what's happening. Okay, so something's happening at visit 2 that doesn't look right. Now, the numbers themselves, the minimum, maximum, I don't see, no outliers kind of call out to me. But there's a problem with the sample size here. So in order to find this out, I'm going to look at a measure that I know is complete at each exam. In this case, it's age. So I know that they had age at each exam. Now, if I'm comparing these, the first exam had 6814. Heart rate was a little lower than that. That's fine. You're always going to get missing. The second exam, I know 6233 people showed up, but only 5,034 have heart rate. That's a big red flag, okay? Because the differences for the other waves is much smaller and expected. So I know I have a problem at visit 2. So I contact the coordinating center and I find out why are so many people missing visit 2 heart rate. And it turns out that, and this is I mentioned before, visit 2 started and they just forgot to collect heart rate, or someone didn't collect heart rate 6 months into the visit, okay? And then they started collecting heart rate. So you just had a huge group of people who simply did not have heart rate. Now, there's nothing we could do about it. They couldn't bring the participants back in. What we want to know as researchers, once we have this, is what makes those people, were those people randomly missing heart rate, which turns out they were, or was there some sort of selection where the first 6 months worth of people looked different than everybody else, right? So it turns out it was kind of randomly missing, just, kind of mistake on the part of the data collectors. And so we're less concerned about it, okay? But we need to be aware of that, and we need to look into the difference between those missing and those not missing. And by the way, how would we consider the difference between them? We don't have heart rate variability, but we can look at other things about them, right? Their age, their demographics, their other biomarkers. Okay, so any questions? All right, so some other issues with data cleaning, our next step in the list of steps was skip patterns. So we talked briefly about skip patterns when we talked about questionnaires. Skip patterns could be a dream for people who are administering an interview, but not a dream for coders or for analysts, okay? Because when you're doing a skip pattern, I'll show you, when you're looking at a skip pattern, you simply have a lot of people missing the next layers of the question. And you need to go back and figure out, are they no's or are they missing? Okay, so I'll show you an example. So skip patterns are often like, you don't know as an analyst if something's a skip pattern, you just see a lot of missing data. In order to determine that, you have to go back to the code book or the original questionnaire and you have to recode. So let's look at an example of a skip pattern. So my original data, this is Midas again. This is Midas Wave 2. This is a phone interview. And I just wanted to figure out the smoking status of participants. Okay, so I look at the distribution. This is a proc-freq, which is a SAS procedure for frequency distribution. It's a categorical variable. And I see that there are 3 options, a 1, a 2, a 9, okay? And these are my numbers. Now, I know my total sample size is 5555. I'm aware of that because I read the documentation. And it looks like, 1 is a yes or a no. I don't know. I got to check. 2 is a yes or a no. Not sure. And 9 is probably some sort of refused, don't know, missing, I don't know. Right? This is how I got it. Okay, so I go back to the code book, and in the code book, not only often code books do this, not only are they telling me everything about this variable, but they're giving me the frequency here. Okay, so 1 is a yes, great. So now I know this is a yes. 2 is a no, fine. And now an 8 is a refuse, but I just happen to have no 8s. That's okay. And a 9 is inapplicable, which is in essence missing, but it's inapplicable usually refers to some sort of skip pattern, okay? So meaning it's inapplicable because there was probably a question before this one that asked another question that said, if the answer is no, skip to the bottom, okay? So that's why these guys get inapplicable, and there are quite a lot of them. So it's about 50% of the entire sample have this inapplicable. So I can't just ignore it. I can't turn it into missing. I need to figure out what they are. Okay, it's too many people. Yeah.
Why do you need to figure it out per se? Those are the people where that question's not relevant to them.
Because I don't know. So if I have 5,000 people, and half of them are gone and have I will have half the people in my sample will have no information on smoking. So if this is a major predictor outcome, that's a huge problem, because I simply drop half the people from my sample. I go from having 5,000 participants to 2,500 participants. And even if it's a covariate, if you put a covariate in your model and it's missing, everyone drops out in the model who's missing on that variable. So you need to worry about missing unless you're totally fine with dropping them out. Now, the other problem, even if you're fine with a 2,500 person sample, there may be some selection issue, because dropping 50%, you need to explain that. Okay, you need to justify. That's a huge number of people. It doesn't make sense.
Right. Well, for this question, I would agree. It doesn't really make sense why it's not applicable, because it's just a general
And also,
question.
we know people will, more than 50% of people will answer this question.
But maybe thinking of like a slightly different scenario where it's not, a question that everyone should be able to answer. But so, for example, in one of the studies I'm doing, some patients get genetic testing, right? But others don't. So if they say, the question is, did they have genetic testing? Yes or no? If it's yes, then we want to know the results of the genetic test.
Right.
But if it's no, obviously they don't have results of the genetic test to input.
But if it's no, so if the next level is the genetic test score, let's say, and you see a lot of missing, don't you want to know if it's because they said no to the first question, or could it be for a totally other reason that they're missing? Meaning, that makes sense. What you're saying is making sense, but you need to investigate to just confirm that what you think is going on, right? That's the whole issue. You might know the data really well and know that. That's fine. You're aware of it. But if I'm getting data from somewhere else, I just need to confirm. So it's a little OCD going on, like, you're confirming everything. But in this case, I know, doing other research, like I know, so for example, income. Income will have a lot of people missing, because people are usually uncomfortable providing their income, or you'll get a big percentage of people uncomfortable providing their income. I just know that working with that variable often. So I'm not surprised when I see a chunk of people missing income. But even for income, if I see 50% missing, that's too many. If I see 10, 15, even 20% missing, I'll go check, but it doesn't, it doesn't kind of like concern me too much. But smoking, I know that that's a problem. So you can, again, it's probably a parent question, but the other thing is, in order to not drop these people and the people you're talking about in your study, I don't want them to have a missing. I want them to have a no. So I'm going to recode them to have a no so that they fall back into my variable, right? So that's what we're going to do. Because if we drop them now, they're gone. I am missing 2,500 people. And that's not what you want. In your case, if you're only looking at the people with genetic information anyway, they're going to drop out anyway, right? You don't want them in there. But in this case, that's not the case. Okay, so what do I do at this point? Well, the other thing I wanted to mention, and this is, if you check anything, check sample sizes, because that will lead you to many, many, many errors, potential errors, and will lead you to really discover discrepancies, either in how your data set was transferred or downloaded, or what data you collected. So I just can check here that this is 4963, but that's a problem. This is what the code book is telling me is in my data set, but I actually have 5555. So what is happening there? I happen to know, I don't know if you remember, but in the MIDAS data set, there's a second cohort of recruited African-American participants from Milwaukee. They were all from Milwaukee. That makes up the difference between 555, 4963. So this code book is a code book that did not consider Milwaukee. So I just need to keep those things in mind because they become relevant down the road. So I find out that that's my original sample. I look to see, I just check to see what's Milwaukee. This is less relevant, and I find out that indeed the discrepancy between the data I have and the codebook data is because of Milwaukee. So how do I figure out the parent question? Well, I go back to the phone questionnaire, the actual questionnaire, which is going to be in the documentation. And I go back to my B1PA 39, and lo and behold, there are a couple questions beforehand. The top question asks, that begins the smoking section, right? At what age did you have your very first cigarette? If they say the age, otherwise they say, I never had a cigarette, and then they jump down, okay? They skip the whole smoking section. The second question, have you ever smoked cigarettes regularly? If they say any form of no, don't know, refuse, they jump down, okay? Now, I want these people back, but I don't want the don't know, refuse people. I want the people that said never had a cigarette, and I want the people that said no, because those are gonna be my no's here, okay? And I want them back. I don't want them dropping out. So that's what I'm gonna recode. So age that they had their first cigarette, right? So the 96 was never had a cigarette. So I want these guys. They never had a cigarette. By the way, look at this big mistake for Midas. So not big mistake, but they'll have 96 can be an age, right? Now it's an unlikely age where you're going to smoke your first cigarette, but it doesn't matter. It's a valid age. So I would not have made 96 one of my codes, but that's what they decided to do. Okay, so these are my never had a cigarette, and there are quite a lot of people, 25% of the sample. And then these are the people who said no to ever smoke cigarettes, and I want these guys folded back in to my new smoking status variable, okay? So I say if this one is 96, smoke is 0. If this is a 2, smoke is 0. And if this is and then that's my never smokers, okay? So I want to know never smokers, current smokers, former smokers. Okay, so that's my never. This is my former. Okay, so they say that they don't smoke don't smoke cigarettes regularly now, but before they said they did. Okay, and those are my current, and that's my final thing. So now I have 5, 5, 5, 5. I have nobody missing. Okay, so recoding. So that's an example of recoding and manipulating the data to get what you need for your analysis. We want to recode separately, aside from cleaning the data and cleaning out the missing, because we want to set up the data that in kind of to inform what we're going to do for our modeling. Okay, so for example, if you are running logistic models, your outcome is binary or categorical, right? If you're running linear regression models, your outcome is continuous. You want to make sure that's really how the variables are set up, or else your models are going to look wonky, or you're not using the right models, okay? And you also sometimes want to explore other ways of looking at the data. So even though I set out to look at, higher or lower levels of education, sometimes I'm really interested in the in-between levels, right? So this is often something that we do in the exploratory phase or the initial descriptive phases of our analysis. Don't be wed to like one form of the data. If you have different options, just look at them, okay? Because it might make a difference. And it will also make you understand your data better. And then the last thing is dummy indicator variables, and that's what we talked about before that I'm going to show you how to use.
Can I just ask you a quick question about the other ways of looking at the data?
Mm-hmm.
I know I learned about this a while ago, but aren't there some types of biases that can be sort of imparted upon the data if you, like let's say it was collected as a continuous variable, and then you decide to split it into two categorical groups, with choosing an arbitrary cutoff. Aren't there potential downsides to that approach?
For sure. So I wouldn't call them biases, but I would call, so for example, if you have a continuous measure of BMI,
mm-hmm.
and then you look at categories, obese,
mm-hmm.
normal weight, whatever. There is a downside in choosing thresholds, mm-hmm. because you might miss the granularity of the data, right? Mm-hmm. So granular data is important. When you, for example, if you consider BMI as your outcome or as your predictor, you're saying for every unit, let's say it's your outcome, for every unit increase in age, okay, for every, let's say age is your predictor. So for every year that someone ages, there's a corresponding 1 unit increase in BMI, okay? That could be interesting or relevant, or it could not be so relevant, right? You may not want to look at one little point of BMI, or let's say 1 point of blood pressure, you know. You may want to look at jumps, and the jumps could be meaningful depending on the variable. In the case of BMI, we know that jumps are pretty meaningful to compare normal to overweight to obese. How those cutoffs were created, that you might want to play with, you know, depending on how standard those cutoffs are. So BMI has pretty standard cutoffs, but you may not, you may say like, you know, I want to try and see if other cutoffs are meaningful here.
But isn't that sort of, I mean, I would be a little skeptical. Like,
You're saying as a process, is that a problem?
yeah, of like, oh, okay, I'm going to try to find the best cutoff point.
So I wouldn't try right. So I'm not doing it to try the best cutoff point, but for example, I'm trying to think of a relevant example. I'm looking at neighborhood, again, going back to this measure of neighborhood level socioeconomic status. So we created this score. Okay, it's a continuous score. But what we're seeing when we fit a linear model is that when you fit a linear model, you are imposing on the data a linear fit. Even if there's no linear fit, a linear model will produce a measure of linearity. If the relationship is in fact in real life not linear, then you're not modeling properly. But you won't know that, right? The program is not going to tell you, hey, Aaron, you're not modeling me properly, right?
I mean, you can get a sense of that just by looking at a graph.
So you can look at the scatter plot, you can look at a low S plot. There are ways to descriptively, if you are really unsure, is this linear, is this nonlinear, then exactly. There are descriptive ways you do it. You say, you know what, this looks linear, I'm going to fit a linear model. Or I have a priori reason based on other analyses to fit a linear model. So that's perfectly reasonable. But you know, when I was doing this research on the neighborhood SES, I was noticing that in the sociological literature, they were talking about these tipping points where there are thresholds, and after certain thresholds, a neighborhood gets much worse. And I said, you know what? Let's consider nonlinearity. Now, how am I going to consider nonlinearity? There isn't a standard cutoff. It's not like a biomarker. So I have to come up with some forms of cutoff. So a very standard way of doing this, instead of picking a cutoff, is to split up the data into quartiles or quintiles, right? And then you can, it's kind of a linear thing, but it's also nonlinear, right? So then you could look to see if certain jumps in the data make a difference. I would go for that kind of approach rather than, like you said, picking a cutoff arbitrarily, or picking multiple cutoffs, right? So if I'm reading a paper and there really isn't a standard cutoff with an ROC curve and all, you know, all this other stuff, then I want to see that they tried it many, many, many different ways, or they use some kind of approach. So you're right. You need some sort of approach, but it doesn't mean because I'm considering sort of different kind of ways that I'm doing it wrong. You know, it really depends on the measure I'm looking at, or, and I don't know if Heather, you have any other input on this, but.
Yeah, I think that's where you just, I don't have much more except to you look a little bit in literature, but I think
You
just have to be, you just have to play around with it a little bit.
And you do have to justify. So
Right.
if it seems willy-nilly, you'll be, you know, taken to task on that. Right.
Exactly.
Okay, so recoding nominal groups. So again, we talked about the fact that if these aren't if these are just put in a model as one variable with values 1 through 6, my model just sees this as ordinal, okay? And it sees it as some kind of inherent order, okay? So what I want to do for nominal groups is definitely group them. And what the next step I'm going to do is create dummy variables, okay? So in this case, I want to just see if people are living with someone or not. So I group it in this way, and I take out the 77 and make it missing. Okay, so why use binary variables? Well, what happens is if I put this DMD MARTL variable in my model, even when I clean out the 77, okay, it is going to, I will get an odds ratio or relative risk or whatever, depending on the model I put in, that is going to tell me every jump you do. So going from married to widowed will give me this amount of risk for my outcome. That same amount of risk will be going from widowed to divorced, or divorced to separated, or separated to never married. That doesn't make any sense, right? Because this isn't an order. So I need to create categories that go in on their own. So that's what a dummy variable. Now, a dummy variable is often what we call a 1-0 variable. So in this case, if I just put in this married variable, I'm going to be assessing the risk associated with being married versus everybody else. Okay? Now, if I create a dummy variable for each of these, I have to leave out one because one is going to be my reference. Right? So in this case, the never married is most likely my reference. And so if I have a dummy variable for married, for widowed, for divorced, for separated, each of these is compared to my reference.
You have to control for multiple comparisons in that situation?
No. And the reason you don't, well, multiple testing is what you do when you're running many, many, many models or many, many different iterations. It doesn't really refer to the number of variables in your model. That's a different thing. If you have many, many variables in your model, then yes, your model can destabilize just because you have more degrees of freedom. But in this case, this isn't so many.
No, I'm talking about like Bonferroni correction.
So that's usually done for multiple testing, which is running multiple models or multiple tests.
But you wouldn't consider like each comparison between each
no, I don't think
individual test?
No, I mean, that's a question for a biostatistician, but no, that's not, because I'm not redundantly comparing them. I'm mutually exclusively comparing them, right? So I'm comparing someone married. If I have a dummy for married, widowed, divorced, separated, living with a partner, I mix living with a partner and married, okay? And leave out never married. That's my reference. So I'm just, in the model, when I look at the married variable, it's being married versus never married, widowed versus never married, divorced versus never married, separated versus never. That's not considered multiple testing. That's just testing each level in a mutually exclusive way and in a non-ordinal way. Okay, so this is how I would set it up. Now, in this case, I mixed divorced and separated together. So in my model, I have one variable for divorced separated, one variable for widow, and one variable for never married. And they're all compared, in this case, to married, okay, because married is what I left out. Okay, so what the important thing to note here is when I created, for example, my widow group, my ones are the 612, but my zeros is everybody else with a non-missing value. Okay, and that way I maintain mutually exclusive groups. Okay, so let's look at some practical implications of how the different groupings can make a difference in your model. So this is a logistic regression model. The outcome is coronary heart disease. And these are the three measures I have in my model. I have age, I have male versus female, okay? And I have race. Now, what does this mean? So male is an odds ratio of 1.2 compared to being female. That makes sense. Age is every year, right? So this is age in years. For every year, I have a 1.048 increased odds not compared to anything. So that's a continuous, right? So every single year gives me that additional risk. What does race mean? It's right. It's nominal, and I've treated it as ordinal because race has a number of different levels in my data set, and I've just treated it right. So either it's 1 or 2, it could be more. I don't know. I just put it all together. So this doesn't make any sense. Now, if I put in dummy variables, right? So I took out the black versus white, Mexican versus white, other versus white. Those are each separate dummy variables. I left out my reference, right? Because my reference has to be left out. So that I know so that I maintain some kind of reference for each of these dummies. And now I have something that makes sense.
Given the fact that you have different types of variables here,
Yeah.
is this like a mixed model? Or like,
No. Mixed model is a different level of observation. So this is all based on individuals. A mixed model will be like you have data on an individual, and you also have data on the place in which they live, or on their classroom, or something nested in terms of levels. This is all individual level.
So combining the categorical versus continuous
Totally.
is using what sort of model?
Nothing. Every model can combine, meaning your outcome is what has to be either continuous or categorical. So if you're running, in this case, a logistic regression model, that's why there are odds ratios, my outcome has to be binary, okay? But my predictors can be categorical or continuous.
Yes, good to know. Thank you.
Yeah, sure. But then I just have to be careful with interpretation, right? So age means for every unit increase of age, in which case I know it's years, because I know the variable. If the variable was days, it would be for every increase in age in days. And male would be versus, you have to just know what variables you have. Okay, so again, another example. So I have age, I have male, and now I have education, high to low education. So how do you interpret this education odds ratio? So this is ordinal, and it makes sense that it's ordinal. So even though it's a categorical variable, there are levels, and it could be, so what this would tell me is that for every level of education, going from high to low education, I have an equal risk conferred upon that level of education. So going from a very high education to a level below, a notch below, will give me a 1.4 odds ratio of heart disease. Then going to the next level will give me another 1.4 risk of heart disease. So every drop, every level drop is associated with an odds ratio of 1.4.
How do you know there are all these different levels? How do you know it's
because
not
I know the variable.
Oh, it's
I
just
created
because you,
the variable.
Oh,
yeah.
because it's not just from looking at that. Because to
No.
me, I would have interpreted that as two levels, high and low, and with an arbitrary cutoff.
Right. So I'm telling you. So good. So
Okay.
I'm telling you that this is, and you're right. I didn't show you. I'm telling you that this is multiple levels. In
I
this
see.
case, it's 3 levels.
Okay, just because.
Yeah,
you
that's
know
just because I know. But you're
okay.
right. You wouldn't know.
Mhm.
High versus low
Mhm.
would be binary. High to low
Oh, yeah.
indicates that there's more than 2 levels. Because versus would mean that it's a binary
gotcha.
variable. Yeah. So I'm just saying when you have a predictor that's categorical that you just put in as a ordinal variable, what the model assumes is that every jump in the ordinal variable has equal risk, which is not an assumption you necessarily want to make. So in education, we don't want to make the assumption, because going from a high school degree to some college and going from some college to a college degree is not inherently equal. And I just know that by thinking about it, right? It's just...
Most ordinal variables you'd want to cut up and compare to a reference, I would imagine.
I think
There's
so.
not too many that would...
There are not too many that would warrant
You're
that.
probably underpowering your ability to see a difference.
But in some case, like Aaron said, you don't want too many new terms in the model, so you may not want 1 million dummy variables.
Yeah.
If you have like 10 ordinal levels, so let's say you have a socioeconomic scale that goes from 0 to 10. You are not going to want to create a dummy for each of those.
Yeah.
But yeah, the more naturally ordinal variables will not necessarily, I can't think of one
I'm thinking
now.
like tumor staging has that problem where they're not.
Right. They're not equal with regard to your
steps are not
outcome.
equal.
Right. There might be some that are, though.
There probably is.
Yeah, there probably is somewhere. So in this case, I was interested in splitting it up into degree attainment that I thought was worthwhile, right? So my reference here is more than a high school education, and I was looking at people with only grade school education and people who just completed high school but didn't have anything more, okay? And those are my 2. And in fact, look at the numbers. So I would come to the conclusion that there's, a 40% greater odds of CHD with every lower rung of education. But when I actually split it up, this is telling me something different. This is telling me that people with only a grade school education have 2 times the risk of those with the highest level of education, and people with complete high school education have 30% greater risk. So I'm actually coming out with different conclusions.
Can I just
Yeah.
throw in one quick thing on
Yeah.
the recoding? Never believe yourself that you did the coding right. Always always do a crosstab of your original variable with your recoded variable. I cannot tell you how many times I've had graduate students come to me and say, but there's, blah, blah, blah isn't there. And I'm like, well, did you check to see why you have so many 9s in this new variable? And they're like, no. And particularly when it comes to how you're going to handle missing. So always get your analyst to give you the table so that you can see, yes, they actually recoded the variable correctly.
Yeah, and that comes to the point. Thank you for mentioning that, because I also wanted to mention, I asked in the beginning who's doing their own analysis. I don't know if you're doing your own analysis.
Some aided.
Right. So, sometimes you get these amazing analysts that will just provide you with this beautiful graph at step number 1. Okay. That is really compelling for you as just great, I can just publish this, send this out to the journal tomorrow. Don't be enticed by this, by the beauty of a graph. You always want to see the dirty output, because your analyst will not likely recognize outliers. Will not likely recognize the other things you want to look at. You don't know their quality assurance processes unless maybe you put them in place with them, but you want to go through all the steps with your analyst. That's really important, okay? You want them to show you some of these things. You want to look at raw distributions always, because that will really help you catch some of these issues. Okay, so I just wanted to show you an example of a summary score. I'm trying to think if I should go through this if we have time. Okay, well, I'll go through it briefly. So we wanted to create a score of socioeconomic status in MESA. And so we just went ahead and kind of looked at 6 different measures that were available to us. The first is income in the top left. On the right is education. So we kind of put it into these categories. For income, we didn't have a continuous measure. We had kind of ranges that people checked off. So they were categorical anyway. For education, we didn't have a continuous measure. We had them say their highest degree attainment. And then we had 4 additional measures of wealth: if they owned a home, if they owned land, if they had a car, and if they had investments. Now, just as we talked about missing, right? So what stands out to you here? I don't know if the numbers look small, but what's my first red flag?
They're not equal.
They're not equal numbers, right? So why am I missing about 600 people for these 3 measures? And how come here it looks pretty good, here it looks pretty good? Income, this looks kind of reasonable because I know that income isn't usually completed very well, and I know about 270 people that looks reasonable. This does not look reasonable, okay? So I go back and I find out that, that in fact, these 3 measures come from the next wave. These come from the baseline wave, and these come from the second wave. So it makes sense that they're missing. But I still want them. I want them in my score. So I'm going to use them. I'm going to set the missing to missing, and I'm going to use them. And I'm going to create a sum of all the items. So as you saw, those are different levels. That's 1 through 4, 1 through 4, 2 levels, 2 levels, 2 levels. So I'm just going to add all these up, the number of levels. And I get to a score. This is cumulative SES, where I have 0 to 10, okay? And I only have 5 missing here. Why do I only have 5 missing if I added it up? What do you think happened to the missings? If I just, so that in SAS you have this procedure where you just sum, and you put in all the things you want to sum. What must have happened to the missing if there's so few missing here? What must have...
Did it imputate it, or...
Well, it's a form of imputation. It did something, right?
Yeah.
So what did it do? So if I did what's called in SAS a proc print, so I want to actually look at the data, right? So in your case in JUMP, you'd actually look at the data, right, at the columns. Just here, I have a 9. Income is 2, education is 3, 1, 1, 1. Investment is yes, that's a 1. Numerically, it just happened to come out like this here. So that makes sense, that's a 9. But here, this is an example of a missing income, and missing car, and missing land, and what does my score come to? A 3. So I know that the software program treated the missing as zeros. It just added across what was available. Now, software programs do things differently. So SAS, when you ask it to sum, it treats missing as zeros. Another program might treat missings as missing and drop that whole score from that person. Then I have to ask myself, is that a reasonable thing to assume that if someone's missing income, that they have the lowest income? Because that's what a 0 means.
No, I mean, they can't be, either you have to impute data or you have to exclude them.
Right, so I have to think about what I tolerate. So when I have scores, how many missings will I tolerate? At which point I will set them. So often, like, we have this kind of arbitrary measure that we say, if you're missing more than half of the components in a scale, we want you set to missing. So in this case, they only have 2 out of the 3. I'm going to set this guy to missing. That's my arbitrary rule, okay? I say it's my arbitrary rule, but when I write up my paper and my analysis, I'm letting you all know what it is, right? So if you disagree with me, you can either do it another way, or you can say, hey, you did it wrong. But I logged it, and I let you know what it was. So that's perfectly reasonable. Okay, so I'm going to skip over that. So some options for missing data. So imputing a 0 is usually the default, okay? Sometimes that makes sense. Sometimes it's simply the best you can do, and sometimes it really doesn't make sense for the data that you have, okay? So that's something that has to be thought through. Multiple imputation methods, what that essentially do, and it's done in multiple different ways, but I'll be done in 2 minutes. Multiple imputation methods utilizes the data that is non-missing that you have available to you and generates through different statistical methods an imputed, like a suggestion for an imputation, an imputed value, okay? But again, this is done in different ways. It's a valid method. It just has to be part of your process, right? And then there's also the option of deleting missing values. Okay, the last thing on my list was just validity of data. I'm just going to show you an example of something that is unreasonable, okay? Not that it's not valid because it couldn't because it's you know, a 99999 or something like that. It's actually input into your data set, but it doesn't seem to make sense. So in this case, I have illogical consistency, and I'll leave it at this. We have 2 waves of MIDAS data. We had a first wave and a second wave, and we asked people at each wave what their highest educational attainment was, okay? Now, it's fine to go from low to high, okay? That makes sense, but what about going from high to low? So these people said that they had some college at the first wave, and then 10 years later said they had less than high school education. That's an illogical consistency. I need to think about what I want to do with those people, okay? These people said they had more than a college education, and here they said 10 years later they had less than high school education, okay? I can't go back to these participants anymore. This isn't my data set, and this is not something I can contact and find out, but as a researcher, I need to figure out what to do. Okay, and then I'll leave you off with some unreasonable values. This is the age that someone had their first cigarette. One person had a 1, right? You need to figure out what you're going to do with those. And then lastly, considering all types of alcoholic beverages, how many times during the past month did you have 5 or more drinks in the same occasion? Okay, we have 31 times. That means that they drank 5 or more drinks every single day of the month. Possible, but you've got to figure out, if you're going to have some kind of cutoff or not. Okay,